All right, today is all about measurements, how we take them, what they're good for, and how we report them. So you can see our objectives are on the board here. The first one is to be able to explain the function and the purpose of the SI system. Then you'll need to be able to derive units from a calculation. So if I give you a calculation and I ask you to solve for density, you'll look at the formula for density and be able to figure out what unit you should have at the end. And then finally, you'll be able to convert between units / metric prefixes of the same unit. All right. To begin with, let's talk about what a quantity is versus what a measurement is. Okay? A quantity is the thing that you are measuring. Okay? Something that has a magnitude, a size, or an amount. So something like volume, or mass, or length. Those would all be quantities that you're measuring. Okay. And in order for the measurement that you take to mean anything, it needs to represent a quantity and it must have a unit to go with it. So a number by itself doesn't qualify as a measurement. If you simply gave me the number 2, that gives me very little information. It needs to come along with a unit, and that unit will tell me both what tools you use to measure this and what quantity you're measuring. So if you report something in liters, I'm going to assume the measurement you've reported is a unit or a measurement of a volume, because liters is the unit that goes along with volume. Questions about what a quantity is or what a measurement is? I'm sure you have had this in previous science classes, but I always like to remind people that if I ask you on a test or on an assignment to do a calculation problem and you don't include a unit, I'm going to dock you points for it. Or if you include the incorrect unit, I will dock you points for it. So make sure you are figuring out what unit you should be putting on the end of all of your calculations. In science class, we have specific units that we're going to use, and they are the units that go with the International System of Units. It's written up there in French because that's the language it was first devised in. I'm not even going to try to pronounce that for you, but in case you were wondering why it's the SI system, that's because in French it's system first and then international second. So everywhere across the U.S., or not across just the U.S., but across science in general, we call this the SI system. It's basically our international system of units that all of the scientists have agreed to use. You read a lovely little document about it for our bell ringer today. So you should hopefully understand now that the reason for this is because prior to the creation of the International System of Units, people used all kinds of different units. And then when they reported that information to scientists from other countries who were not familiar with those units, it became difficult for them to understand what they were reading. And so somebody thought, we should have a standardized system for science specifically of units we are going to use when we do our calculations, when we do our experiments, and when we report our data to other scientists. This is the system we're going to use. And so they got together, they had a convention, and they worked it out. Okay? We call it the SI system, and it's the one we use now. Okay? There are 7 base units of measurement that we use in the SI system. Okay? And I'm going to go over them with you. They're in a chart on the next page here. So the first one, the quantity that we're measuring is length, okay? And the unit we use is the meter. This is the base unit. I'm going to talk to you about what that means when we talk about prefixes here in a moment. But this is the base unit. And the abbreviation we use for it is a lowercase letter m. So if you were going to write out, 20 meters and you didn't want to write the full word meters out, you would abbreviate it with a lowercase m. we use mass, we use the base unit of the kilogram, and we abbreviate that kg. Okay. You can also see that each quantity has a symbol that goes with it. Those symbols are going to be things you're going to see in equations. So you have probably seen this if you were ever doing, like area is length times width. Length is a lowercase l, okay? So as we learn different equations, you'll see some of these symbols used to represent them so that the equation doesn't take as much space to write out. Time, we use the base unit of a second, and that is the letter S. Temperature, we use the unit Kelvin. So this is different. You've probably heard of Fahrenheit and you've probably heard of Celsius, but chances are you have not heard of Kelvin. Kelvin temperatures are going to be way different than temperatures that you're used to because they base them off of absolute zero. So 0 on Kelvin is actually absolute zero, where an object has like no heat or energy left in it of any kind. So the temperatures there are going to be a little bit different than what you're used to. It's not uncommon to also see temperatures reported in Fahrenheit and Celsius, but just know that for the SI system, Kelvin is the one we use. Then if you're doing amount of a substance, then you're going to use moles. We're going to use moles a lot in chemistry. We're not getting to them quite yet, but when we talk about an amount of substance, we use moles. And then ones that we are likely not going to run across very much this year is electric current, which is measured in amperes. I can never pronounce that word correctly. And then luminous intensity, how bright something is measured in a candela. And those have the symbols capital A and then CD, respectively. Okay. But like I said, we're not using moles yet. We'll get to them later in the semester, and we likely won't hit on electrical current or luminous intensity very frequently. So before we talk about things other than base units, let's talk about a couple of concepts that we need to clear up. The first is that mass does not equal weight. So here, in common speak, when you hear people talking about mass and weight, they tend to correlate them and make them the same thing, but they are not in fact equal. Mass is the measure of the amount of matter that an object has, and we measure this with a balance against a kilogram weight, which is based on the standardized kilogram weight that's kept in a very special jar in another country. I can't remember which, but that's the standard against which we measure things. And so we balance the scales to figure out which things have that same amount of matter in them. Okay? The difference between this and weight is that weight is a measure of the pull of gravity on that object. Okay? And we measure this using a spring scale because we're measuring the downward force of gravity. Okay? No matter where you go in our solar system, your mass will stay the same. You will be made up of the same amount of matter. Unless you chop an arm off or get liposuction and get a lot of mass removed from your body, okay? But even though your mass is going to remain constant, because the force of gravity is different in different locations in our solar system, your weight can fluctuate and change based on the force of gravity. If for some reason we woke up tomorrow and the force of gravity on Earth had gone down tremendously, your weight would be significantly less, but your mass would have remained the same. Okay? So that's the difference between these two. When we have a number that is either too large or too small for the base unit to make sense, we're going to use a prefix. Okay? So imagine you were trying to measure the distance between here and Norfolk in meters. It's going to be a very, very large number, right? As if you imagine a meter is like 3 feet, essentially. So if you're measuring the distance between here and Norfolk in meters, you're going to get this very large number that's going to be very hard for people to mentally understand and for you to use in calculations. So we might use a prefix on it, okay? There is a table of common prefixes available in your book on page 39, and I also am going to put it up as a material on Google Classroom. And I'm going to bring it up right now so we can kind of discuss what it looks like. Okay. So here is the chart that I was talking about. Zoom in a little bit, okay? So imagine this space in the center that's blank is the location where you would put your base unit. So if we're going for the unit of length, then our base unit can go ahead and be the meter. Okay? So if we wanted to express this in a number that's going to be less, we might express it in kilometers, or you might have heard people refer to that as kilometers. So by sticking that prefix, kilo, on the front of the word meter, then we are changing our number. So let's say you had 1,000 meters, you would only have 1 kilometer. Okay? It increases it. So for every kilometer that you have 1,000 of your base unit. Okay? If you had a decameter, you would have 10 meters. So that is how you read this chart to help you. Okay? And we're going to practice towards the end of this lesson, we're going to practice converting between base units and metric prefixes, which is what these are. Prefixes also work the other way. So if I have a very small measurement, okay, so, you know, if I had 0.000 meters, I could, instead of calling it 0.000 meters, I could just call it, why is this not exiting out of the drawing tool? Thank you. I could just call it a millimeter instead of 0.001 meters. I could say I have 1 millimeter. So it does go smaller as well. This gives you the exponent, it gives you the actual numerical meaning, and it gives you an example on the side to help you understand each prefix. I will go ahead and tell you that we tend to use centi and milli pretty frequently, and we tend to use kilo pretty frequently. The other ones are not as common, but you may run across them in practice problems in your textbook. Okay? This document is going to be shared with you on Classroom as a material. You always have access to it, and on some tests, not all tests, but on some tests, I will provide you with this. All right. In addition to using metric prefixes to change base units, sometimes we also combine base units to get what we call derived units when we measure values that are a combination of quantities. On the chart that follows, we're going to talk about some common derived units. Okay? So, for example, the quantity area is a combination of length and width units. So we are going to derive our unit from the equation. Take a look over here. We have length, which we know will be measured in meters, and width, which is another length, which will be measured in meters. So when we take meters times meters, we come out with meters squared, which, as you can see, is our derived unit. Okay? So when we say derived, we mean we are combining different units to get this. Okay? So volume, you could have the cubic meter, okay? Because it's length times width times height. You will all notice also that in the SI system, we use units of milliliters cubed. milliliters or liters, okay? So those are other units that we use with this. This is because, I'll explain this to you. So you'll recall the prefix centi is a portion of a meter, so centimeter, okay? When you take centimeters times centimeters times centimeters, you get centimeters cubed, and that is equal to, so 1 centimeter cubed is equal to 1 milliliter. So that is how we make that jump between a centimeter and a milliliter. Okay, milliliters are more common units of volume for liquids. So liquids or gases will tend to be measured in milliliters or liters, and then solids may be measured in centimeters cubed or in meters cubed. Density. So you'll see density is calculated by taking your mass, which should be in kilograms, and your volume, which should be in either meters cubed or centimeters cubed or milliliters or liters. And so you're going to get, let's say meters cubed. You're going to divide them, and so you'll notice that your unit is just kilograms divided by meters cubed. You might hear people say that as kilograms per meter cubed. Okay? That's what the per is, that slash, which is essentially just a division. Okay? Then we have molar mass. So when we learn about moles, we'll talk about what a mole is, and when you are taking the mass of a substance in grams divided by the amount of that substance in moles, you'll get a unit of grams per mole as your derived unit. And then the same would be true for molar volume. And then we get down to energy, which has a pretty complicated unit, right? You can see the unit here is kilograms divided by meters squared per second squared. And that is because force is in newtons, which is kilograms times meters per second squared. And then we have also distance, which is meters. So we're going to start, you see how we can take some pretty complicated units and mesh them up, right? To get our derived unit. Sometimes derived units are also given a special name. So you'll notice up here we just have the square meter, right? And it's just meters squared. But down here we have kilograms divided by meters squared divided by seconds squared, but we're calling that a joule, right? So sometimes they will be given their own special name, and then you might get an abbreviation, that capital J, that you can use instead of this big, messy thing. But you should, even if you didn't know what a joule was, if you knew how to solve for energy, force times distance, you should theoretically be able to come out with the correct unit by simply following the formula and combining the units in that way. If the formula says length times width, and you know length is meters and width is meters, you should be able to come out with meters squared as an answer for your unit, even if you didn't know that the unit for area was meters squared. Okay? Because you should know it should be meter times meter. Okay. When we measure volume in the lab, cubic meters are too large, so often we use other units. We can use centimeters cubed. There are 100 centimeters in a meter. That means there are a million centimeters cubed in 1 meter cubed. Okay. A liter is equal to 1,000 centimeters cubed, which means there are 1,000 milliliters in a liter. And because of this, 1 centimeter cubed and 1 milliliter are equivalent units, so we can interchange between measures of solid and liquid volume in this way. I'm not going to expect you to remember all of the numbers that we put up here. I'm just showing you the math that works out to help you understand why a milliliter and a centimeter cubed are equal to each other, so that you can understand why we use both meters cubed, centimeters cubed, milliliters, and liters as measurements for volume. We're also going to work with density a fair amount. Okay? Density is your ratio of mass to volume, so you get your density by taking your mass divided by your volume. It's an intensive property, so if you remember what that means, it means no matter how much of a substance you have, its density will always be the same, even if you have a very small amount or a very large amount, which is useful because that means we can use density to identify materials. If I have an unknown substance and I'm trying to figure out what that substance is, one of the calculations I should run is density. I should measure its volume and measure its mass and calculate its density, and then I can compare that density to a list of known densities. But you'll need to also note what temperature you measured the density at, because changing the temperature can cause objects to expand and contract, which means their volumes could be different at different temperatures. And because density is equal to mass divided by volume, if you change the volume of the matter, you're also going to change its density. So you have to note what temperature you're measuring density at. We're going to do a little practice with density here. Okay, you have a little practice problem. In an experiment to identify an unknown gas, they find that 1.82 liters of the gas has a measured mass of 5.430 grams. Go ahead and calculate for me the density of the gas, and you can leave your units in grams per liter. So for this, we need to remember our equation for density, which we said density was equal to mass divided by volume. So then we're going to plug in our numbers here. Our mass was 5.430 grams divided by our volume of 1.82 liters. When we do that on a calculator, what do we come up with?
2.98.
We'll go ahead and round to 2.98 for now. And we will call that grams per liter because that's the unit they told us to leave it in. You can see that right here, right? Grams per liter. That's where you found your unit there. All right. We can use conversion factors to help us change between units. I mentioned this briefly earlier, okay? A conversion factor is just a ratio derived from the equality between units. So what you're going to do is you're going to figure out how much of one unit is equal to how much of another unit. Because they are equal to 1, you can multiply them times other factors without changing your equation in any way. You're going to use the quantity sought is equal to your quantity given times your conversion factor. And that's going to get you to the correct units that you want. This all sounds very abstract, so of course we're going to do an example to help this make sense. Okay? So, if you look at this, okay, we have 1,000 meters is equal to 1 kilometer. So they are the same. 1,000 meters is the same thing as 1 kilometer. You'll notice that I have also written this flipped upside down, where 1 kilometer is equal to 1,000 meters. And that's because depending on what unit you start with, you will need a different version of this to help you convert. You can see this example down at the bottom here. Okay, notice we start in kilometers, and if we want kilometers to cancel, then we need a conversion factor where kilometers is on the bottom, and we are dividing by it so that this cancels with this. okay? And then because 1 kilometer is equal to 1,000 meters, this is essentially like multiplying times 1. So we're not changing the value of what we have, we're just changing what units it's expressed in. When we take 17.5 times 1,000, we convert it from being in kilometers to being in meters. So 17,500 meters is equal in value to 17.5 kilometers. Sometimes when we do conversions like this, you'll be converting between metric prefixes like meters and kilometers. Sometimes you might be converting between hours and seconds, where it's not so much a prefix. And in that case, what you need to know is how many seconds are there in an hour. Okay. For the sake of time, I'm going to run the following practice problem for you on the next page. Okay, we ran out of time, so I will not assign the homework today. What I will do instead is ask you to try the practice problem where you're going to convert from 5.712 grams into both milligrams and kilograms. Try this on your own, and we'll start with this as our bell ringer tomorrow, okay?